All right, good evening. Welcome back. So let me remind you what we have done last week. And as I sent a message today, we should be able to do and finish Kalman filter today if we are lucky. So I just recall Bayes' theorem, and one application of Bayes' theorem is this equality. Whenever you have two random variables on the same probability space, you can express the density, the PDF of x1 knowing x2 with such a formula. And what you can see, there is a relation between the probability density function of x1 knowing x2 and the probability distribution function of x2 knowing x1. This is at the root of what we are doing. Then I recall the inference theorem, the inference model. The observation is a function of our system plus an observation error, and H is called the observation operator. And if I just apply this for x1 is equal to capital X, x2 is capital Y, we end up with this formula. And in this formula, what we should keep in mind, this distribution is called the prior distribution because so far we have not done any measurement. Y is the measurement, while this one is going to be the posterior distribution because it's conditioned with Y, which has been measured. And this function here is called the likelihood function. Now, I slightly change even in the notes, the notation. I think it's better now. These two notations are equivalent, except that when I write x of a, I consider a as a random variable. And implicitly, I already take into account that y is known. So you can see there is no more y. I just write the density probability distribution function of xa, which is a for analysis, without writing y. Y is implicitly taken into account. Is proportional to this likelihood function times the probability density function of the variable x before any measurement, so we call it xf, just to make a difference between x when y is known and when y is not known. So I think this notation is better than the one I introduced last week. Then I developed one example when we suppose that x follow a normal distribution. This observation error is Gaussian, so normal distribution centered at 0 with this covariant matrix R. And if we assume that H is linear, so it's just a matrix, then we did a computation and we end up by using Bayes' formula that this random variable follows a new normal distribution with some expression for X, A for analysis, and P for its covariant matrix. And I gave this formula last week. I have introduced now a shorter notation with K, which is called the Kalman gain matrix. Last week, I didn't introduce it, so you just have to replace K by this expression. And thanks to Vic, we have a proof of a formula I have used. So on the website, you can find a proof of what is called Woodbury formula. Sometimes it has 3 names. But I think this is a correct name because he's the one who generalized it. These formulas will appear again today. So it's only based on a certain model, which is quite simple, and Bayes' formula. So we have some observations. We can deduce a new probability density function for xa. Then I just mentioned, and I'm going to be quick on this, this gives us a distribution. If we want to have a point estimate, so it means not the distribution, but just one value, I introduce this loss or cost function, and then we can get a number by a certain formula, which is very general, which is called the Bayes estimator. And I gave 3 examples of such formula. I think this is just one way to put everything in one framework. Either the posterior mean estimator, which is when you use a certain function square. When you use a function with a norm, but not norm square, you get a posterior median. And this one means you just, when you have your distribution function, you take the value, which is where your probability density function take a maximum. And then I wanted just to mention something about sampling. So I have started this section. First, this is a general definition about two measures. We say that one measure nu is absolutely continuous with respect to another one if when you measure a certain set, it's zero whenever this one is also zero. And if you think about density, it simply says that, if you think about it, if one vanish, let's say one vanish, if the probability density function time mu vanish, then the other one has also to vanish. Otherwise, this cannot be satisfied. Now, whenever we have two or one measure is absolutely continuous with respect to the other one, it means we can express this one as an integral with a density function, and this density function is called the Radon-Nicotin derivative. So this has nothing to do with our course, but this is just for general information. And now if this measure is absolute, it's correct that I used 2 times the same word. It was absolutely continuous with respect to another one. Now, when I say that this one is absolutely continuous, it is absolutely continuous with respect to the Lebesgue measures, a measure you are familiar with of calculus 1 or 2. So if this is an absolutely continuous measure, so it means if when you measure a set, it is just obtained by the integral of density times the Lebesgue measure, then you can get also a density for the second one. It's a little bit complicated, but we will just see why I needed to introduce this. Is there any question about what we have done last week? It's a little bit orthogonal to the main direction, but I want to give you one result which appears in different frameworks. And by the way, even if this is not absolutely continuous, but if you have a measure taking point values, take this something similar to this. I just wrote it in the absolutely continuous case. Yes, I am recording. Yes. You were not listening. No, it was noisy at the beginning. Okay, so what I want to, this is the result I want to give you, which is called importance sampling or importance sampling. And you might see this in application in physics or elsewhere. So let me explain. So let x on x prime be random variable. With values, I keep the general framework, I call it lambda at the very beginning of this course, but this can be Rn, this can be a discrete set or a finite set. And so that for any random variable, we have introduced the law, which is a measure. The law of x is absolutely continuous. With respect to the other one, so with respect to mu x prime. We are in this framework. Let G be from this to this space, which I have also introduced already a long time ago, but you can think about this either as R, Rn, or matrices, n by n matrices or n by m matrices. I just need, whenever I write measurable, you can just replace this by continuous, because in application, we always use continuity, but this is slightly more general. Now, if we have, now it's about sampling. If we have xj a sampling following mu x. So think about an experiment when mu x is a distribution, but you take some values according to this distribution. So a sampling following mu x, and you have another sampling, J prime, following the sampling following mu x prime. Then this is the conclusion. The expectation of g of x. Wouldn't be surprised that I can write this as so when you have a sampling following a certain distribution, and if this distribution is related to x, then the expectation of a function of x is given by you take g of your sampling, you sum these values, you divide by m. But now suppose you don't have this, but you have the one with the sampling with x prime. You would like to compute this quantity with a sampling from x prime. It turns out that you can do it. It's a sum over j, but you need to add some weights. And what are these weights? J is equal to oh. Okay, I have taken an assumption. So all right, so let's look at this. What I'm saying is when you want to compute this expectation based on a distribution or sampling following x, you can do it with a sampling based on the distribution of x prime. If you put some weights, and these weights are given by this ratio of the probability density function of x divided by the one of x prime at the same point. No, precisely it's a certain number, but you normalize, it's a normalization. Look, indeed, the denominator contains the same expression as the numerator, but with a sum. So it means the sum of the weights is going to be 1. So you can look at this as a normalization. Because now the weights, the sum of weights is equal to 1. This is why we normalize. Now I finish I x prime are the PDF or the PMF. Of x and x prime. So you can do this either in the absolutely continuous case, and then you end up with a PDF, or in the discrete case, and then these are probability mass functions. Yeah.
So omega, isn't that like pi x of xj is a basic like for the numerator of the both sides?
No, I think it's everywhere it's small x prime, because this is the distribution you have, or the sampling you have. You have only, the use of this formula is if you don't have this expression. So you want to have everything in terms of another distribution, which is x prime. So let me just, this is really used when you would like to have a distribution, but you don't have it in your catalog or in your computer, you can construct one distribution like this. So let me just write one sentence. This approach is useful. We need distribution of x while only the distribution of x prime is provided by only distribution of x prime is provided. This important sampling is useful. And a remark, I will use it in the next formula. What is this ratio? If you think it's no more on the blackboard, but this corresponds to the function rho I have introduced before. X prime j divided by pi x j prime. This corresponds to this rho, which is this Radon-Nikodym derivative. It is a relation between the two distributions. Sorry, no, this is one. There is a prime here. Otherwise, it would be one. Yeah. Why? So this rho was a Radon-Nikodym distribution. Now let me explain why I have introduced this. So in our framework, this is an application. In our framework. Inference problem. Remember, this is what we are doing now when we want to estimate x knowing y. This is called the inverse inference problem. And in what we have discussed, I have already written today the formula proportional to this likelihood function. So you recognize what I had written before when so proportional means there is just a constant in between. So if you can replace this by constant, you can replace it by equal a constant time the other thing. But this is what I have written before for one PDF is equal to a density times the other PDF. It's exactly this formula. And the midterm, this term was rho. So once you observe that we are exactly in this framework, what we get, so we get for any G from with I try to be general. From Rn. We were in Rn in this problem here. We get that the expectation of G of XA, which is random variable corresponding to the analysis. So after the observation is given by, I just copy what we had before, but now in our framework, I replace the row function by this. X time G of XF. It is XJ. XJF G of XJF. And I need to normalize, remember before, it's still there. The weight has to be normalized. So I have to divide by the sum. I need to take another variable k from 1 up to m of this pi y. The denominator is again a normalization, such that the weights are sum up to 1. So this is a formula which is also useful. We can get an expectation of a function of the analysis random variable, what we want to get, by a sampling of the original or the prior or the forecast multiplied by some weight and then take the sum over a sampling following a certain distribution for X for the forecast. So if you put everything together, this is directly an application of what I have introduced, this formula, which was visible before, and this important sampling. And I should just finish the sentence.
Excuse me?
Yeah.
I have a question.
Yes.
So you just cleaned that part. I have a question about the xj prime. They are resolutions. So we can say that pi x prime of xj prime are hardly to be 0. And then since these two measures are absolutely continuous to one is absolutely continuous to another one, so it promises another one is also hardly to be 0. So that's why you didn't give an assumption of the denominator is not 0. Is that the reason?
You mean this denominator?
Yes. No, not this one. The one on the right.
Which was here.
You have a ratio on the numerator and also on the denominator.
Yeah, but you're wondering why it's not 0.
I understand the denominator of the denominator. Both denominators are not hardly to be 0. And then both numerators are also not 0 because of the absolutely continuous. Is that true?
I guess so, yes. If one of them is not 0, the other one has not to be 0 precisely because of this absolute continuity, yes.
Okay, thank you.
Yes, it was in the assumption that
I know the x is absolutely continuous with respect to x prime, but
yes,
everything you wrote, x prime is continuous with respect to x.
You don't need. One is absolutely continuous with respect to the other one. It's not going in the two directions. But the one on the denominator should be the one which is not 0.
The x prime.
Yes. And so the end of the sentence was where this sampling xj prime is a sampling following the prior distribution, following something mu x prime. Or mu is, it is f. Yeah. Yes.
What happens if it's 0 and both are 0? So like it becomes 0 over 0.
You forget it. Nah, if everything, I mean, it's a sampling. So if one value is 0, you can always reject it. I cannot say much more than this right now. Where are my notes? Okay. Okay, I wanted to present this. It's not really necessary for now, but yeah, this important sampling, as I said, is something useful. Okay, now we have done enough mathematics. We can really work on some concrete data assimilation model.
Sorry, I guess there is a mistake.
Where?
You didn't introduce xj prime. Here you use the resolution are xjf.
I didn't. Sorry, it's a f here. This is your question?
Yes.
Okay. Sorry, it's a f. In the abstract theory, it was a prime. When I use it in the application, I replace prime by f. Thank you. I hope there is no mistake in my note. Basic algorithm of data assimilation. So I recall and slightly modify one thing. We'll see on slightly modify. But the modification is very simple. Slightly modify the framework. What we have, it's a discrete time dynamical system. So I always have this f from Rn times z to Rn. We have a family of random variables, which are IID. So it means independent and identically distributed random variables. N is going to represent the time. And we have also a family Xn, discrete time, Markov process. So it's also a family of random variables, but they have a special properties. When you study Xn, if you know Xn minus 1, you don't need to remember the rest of the story. So if you know just what happened the previous time, you can reconstruct, and you don't need, the previous information doesn't bring anything. This process with value in Rn, I can just, to be consistent, I need to specify this. What was the discrete time dynamical system? I have already introduced it from the very first lecture. It is this, but at that time we had no random variable. So you can see the small difference. The small difference in the first lecture, I called this f of xnn. Now, sometimes it's better to write it like this. And what is the purpose? Is simply that if you write it like this, you emphasize that xn plus 1 is not very different from xn, which means at one point you can say f is a small term compared to this 1 times xn. This is just a point. But you can also call this function, in fact, this is identity function plus f. If you don't want to write it like this, you can just call it xf also. But I will use it at least for now. It doesn't make a big difference. Now, so this is the discrete dynamical system. Now we have some observations. And I want to be, at least at the beginning, a little bit more general, in the sense I don't need, if you think about n as a time, you don't need an observation every time. Maybe you have an observation at time 1, 3, 5, 7, and so on. I'm not imposing from the beginning that we have an observation at every n. So I'm going to say for certain time t1, t2, up to tk, they belong to Z. There are also some time, but maybe not 1, 2, 3, 4. For H, this observation operator, we have a choice. Either we take it independent of time, or it can also depend on time. The observation can be time dependent. So if I want to be general, I should also say that it can depend on time with value in Rm. This is already what I have written. Maybe I should emphasize this Z here and this Z here if the system is not autonomous. Most of the time we take it autonomous. So it means not explicitly depending on time, but for free, we can take it non-autonomous. So for blah, blah, blah. And this, I also need a observation error. But this observation error is taking place whenever we have an observation. That's why I index it with these tj. And they are IID random variables with value in Rm. Independent and identically distributed. So they follow the same distribution, but they are independent. And we said, now what I have already written, y at tj is h at x tj and time tj plus epsilon tj. So now we have the framework on these 3 columns. This is the dynamical system. And these are the observations taking place at some time. Maybe all n, maybe less frequently. And if you check, this is a random variable with value. It's a random variable with value in Rm, because the right-hand side is taking place in Rm. So it's the same as what we had at the beginning, but at that time we had not the language of random variables. It was a deterministic system. This is a probabilistic system. If you compare precisely with the first lecture, since this is also called a perfect scenario. Can you guess why it's perfect? Except that it is very nice. Perfect scenario model. Can you guess? But something is missing compared to the first lecture. The first lecture, y was not directly related to the x, but there was a function g, which was this model error. In a sense, the model error, there is no g, but now we have this error here. But nevertheless, it's called a perfect scenario model because in the observation here, we have directly our model, and we don't have something more complicated than the model. So, since no G, you can check up here. So it means truth is equal to the model. You can check at the very beginning on page 5. When I write page 5, it means page 5 of my notes. All right. Now, so this is a framework, quite general framework. Now we are going to suppose we have some observations. So I'm introducing a new notation, T1 2.tk. This is a notation. What is this 2 dots? These 2 dots here. This is the same as y ops T1, T2, T3 up to tk. So these 2 dots mean simply you list everything from T1 to tk. What is it? This is y T1, comma y T2 up to y tk. And in fact, this is nothing but a matrix. It's a matrix. We have m lines because each vector is m-dimensional times k column. This is just one way to encode k observations. This is called a matrix, observation matrix. So what we are interested in, as we deal with the inference problem, we are interested in the distribution of xn, knowing yeah. Okay, let's check what is the meaning of this. Why I added a Tn. We are interested in the distribution of this random variable xn, but since I have not imposed that it is autonomous, everything can depend explicitly on time. So this is, again, I should underline it in yellow. It appears if the system is not autonomous. If you think about, if you want to simplify, you just forget it. So autonomous means usually your physical system is isolated and nothing takes place from outside or nothing interferes from outside. So this is what we are interested in, this distribution of xn, which could depend explicitly on time, knowing for having some observations. But there are different situations, and I need to introduce 3 words. It's not correct in my notes. I should write if n is bigger than tk, n is about tk, and n is smaller than tk. Oh, no, smaller than t. Yeah, tk. There are 3 cases. So if n, in my note I have written tn, but in fact this is better n because we have a n here. If n is bigger than all observation, it means we are forecasting something. So if one speaks about a prediction process, because the observations stop at one point, but we want to know something in the future or after the observations. This is the first case. The second case is if the observation and the tk are about the same or are the same. One speak about a filtering. This is the word I wanted to introduce. One speak about a filtering problem or filtering process. And the third one, if n is smaller than tk, what does it mean? It means you want to know the system in the past, after the observation. So observe the Earth today, and you want to know how it was 1 million years before. We have the observation of now, and we want to anticipate what happened before. So this is called the smoothing process. If n is smaller than tk, and speak about a smoothing process. And the tools are slightly different. We will mainly concentrate on essentially on this one and on this one. But sometimes the smoothing process also appears. So this is a prediction process when we do it in the future. This is a on-time process or filtering process. And this is a kind of backward in time process. So I'm going to concentrate first in the second case. If you have any question, of course, interrupt me. These are just words. Now, what about the filtering process? The next section is the Kalman filter. I'm going to suppose in the model I have just recalled, we suppose that the model error, what was called epsilon, follows normal 0. What does it mean? It means your error, when you do the observation error, it's on average, the average is 0, the error average is 0, but it has a certain covariance.
So is that the model error or the observation?
Yeah, it is the observation error. And in my note, I have even written measurement error. So no, it's, yeah, it is. Let me just check, but I think epsilon was observation error. Yeah, observation. Thank you. And remember, I have introduced epsilon n because it depends, or tj. But since they are all identically distributed, it's enough to say that the model of all of them follows this distribution. Okay. So suppose that, and I need to suppose one more thing. That observation. I will say a little. So I'm now assuming, and I will explain just why I can take this assumption, that the observations are taking place at every time. It seems that it's less general, but in fact is not. It is not so much less general. So I assume that the observation is not good. Oh, yeah, they follow. Tj is taken at time j. Then, by Chapman-Kolmogorov, which I have introduced 2 weeks ago. And I can do it because I suppose that we have this Markov process. So Chapman-Kolmogorov tells us that this density distribution of x1 I keep this one for what I'm writing now. This is the same one because it might be non-autonomous. It is the integral of pi x1 of x1, 1 knowing x0, 0 times pi x0. X0. This is Chapman-Kolmogorov. It tells you this density is given by this one, knowing x0, and you multiply by the density of x0, the probability density function of x0. This is Chapman-Kolmogorov. I would just want to emphasize this is in fact your initial condition. We have no measurements at that time. And this is called, I introduced it, I denote it by P. And this is called the Markov kernel. Now, if I want to be precise and if I want to be consistent, I should somewhere write a 0 because it depends explicitly on time. This is the difference between autonomous and autonomous. If it depends explicitly on time, you have to keep track of it. If it doesn't, all the p's are the same. So this is always the same. You can forget it. All right. If you think about it, this is nothing but P x1f at x1, 1. I want to emphasize this is a focused, we have no observation so far. Okay. Now, this is Chapman-Kolmogorov. Now, by Bayes. Bayes theorem. By Bayes' theorem, we get the following thing. This distribution x1, x1, 1. Knowing y1, I suppose now we have y1, so we have a first measurement. This is equal to, so now I'm just copying what we had before, y1, adding this small one just for fun. This is Bayes' theorem, and I need a denominator. So in order to give us a probability distribution function, I need to divide so that it gives us, the integral gives us 1. Again, you can think about the denominator as a normalization. Bayes is simply this density x1, y1 is given by y1, x1 times the density of x1 divided by a denominator such that it's normalized. And you can think about this with the notation I have introduced today. This is pi x1 analysis x1. And when I put analysis, I can forget the observation. This is just a notation. Okay, what we observe is that one guy is given by this. This appears here. So it's going to be an iterative process. You first compute something, you inject it somewhere else, then you use your result to the next expression and so on. Okay, so this expression here, which can be computed from the initial distribution plus this evolution, maybe I should write Markov kernel related. It's related to the dynamical system. Yes, here. So this expression appears here now. What about this guy? This guy is, I need to say something about it. And is our assumption. So what is our assumption here? Our assumption is that this one about the noise. The noise follows a normal distribution centered at 0. We have that pi y1. So, y1. So if it is, I use now that this noise is Gaussian, and this is something we have already done once or twice. If it is Gaussian, I can write this expression and I end up with this one. So it's this factor time exponential of -1/2 of y1 minus. There is a transpose somewhere. And probably one more parenthesis. It's the exponential of everything. Now I'm using here the assumption about Gaussian noise because this is a formula, this is a distribution, probability distribution function for epsilon. And we had this relation y was h of x plus epsilon. This is exactly what we use. Now, if x is given, we can relate y and epsilon. I have to be a little bit more precise. I should add some n. but this is what I'm using here. I'm using the exact shape of this distribution for epsilon. Right, so if we have this, now I can compute this term because this was introduced at the first step. This one is given here, so I can compute this one, which is the analysis of X1. And now we can go on. So I'm going to do one more step, and then I give the general formula. Now, I do the same structure by Chapman-Kolmogorov. We can forecast X2, which means I can write pi X2 of X2 knowing Y1. It's a focus because I'm using only the single observation, not 1 and 2. I forgot to write, this is an integral over Rn because we integrate X. Integral over Rn on X2 of it's very systematic, so you don't have to think so much. This one, Chapman-Kolmogorov tells you it's given in terms of X1. But X1 was given once, X1 analysis was given when X1 was, I can write it slightly differently. You can, maybe it's better. X2 knowing X1, 1. This is what I call X1 analysis of X1. It's the same. But I just want to emphasize that the next step, the forecast, is based on the analysis of the previous step. And what we recognize, this is similar to, I should put a 2. I want to be consistent. There is a 2 here, comma 2. This term is what I called P, or if it depends explicitly on time, P2. But this is a Markov kernel. It's the same structure given by the dynamical system. And now, so this, I can call it pi X2 focused of X2, because it's a focus since we don't have yet the second observation. I have already used the first one, but not the second one. And now with Bayes' theorem, I'm going to compute pi X2 analysis for X2. Then by Bayes' theorem, we get pi X2. I can just write analysis of X2. Or maybe I keep first the notation with the X2 knowing Y1, 2. But with the new notations about the short notation, this is nothing but pi X2 analysis of X2, because the analysis is taking into account this observation. So by Bayes' theorem, I know that this is, if I do some mistake, please let me know. Pi y2 of x2, 2. And the denominator is the integral like we had there. It is the integral of the numerator. So it is the integral on Rn of okay. So you observe that it's exactly the same form as was the first step. All right. And so I can write the general formula. What is, so if you think about it, we have not imposed so much. We have imposed something about the noise, the observation error, but still the Markov kernel is very general. And it will simplify a lot once I'm going to impose the simplest situation, linear evolution. So general formula. It's only, I'm only using Bayes' theorem and the Markov process. So the general formula, I can see some small mistakes in my notes, so I will correct. The analysis of xn is given by integral over n. Yes, I should copy correct it, the forecast. Thank you. But there is, the 2 is not correct somewhere. So the forecast n knowing it's n minus 1. And here, this is the analysis xn and dxn. I hope that, and if I want to be consistent, I should put an n here. Yeah, okay, probably it is too complicated to keep, but probably in some situation, it's good to remember that the system is not time independent. I guess I can keep this 1 here, x n minus. Okay, sorry, I need more space. Analysis of x n minus 1 at time n minus 1 dx n minus 1. And if I want to be consistent, I should put n minus 1 here. Okay. So you for the focus, you need the analysis at the previous time. And this is related to the Markov kernel. This is Pn. Oh, yes, I guess Pn. And the second formula you get is by Bayes' theorem, you get pi xn analysis of xn. So this is when you take into account all observation up to time n is given by this ratio like here, pi yn of And then I should write xn focused xn divided by the normalization factor. So it's again the integral of the numerator divided by integral on Rn of I. It's okay. It was complicated to write, but now we have this formula for a general situation. And so the Kalman filter will be just an application of this. Let me just add one word. This is called sequential data assimilation, because we do it every time we have one new observation, we update our system and so on. But we don't say, in this approach, we don't say anything between this pi xi a and pi xj a. So we have no relation between different times. And this can, and probably we will discuss this at another time. So 2 ingredients, Markov process, I use it in the second, no, in the first. This is based on Markov process, the fact that once you know what happened the previous time, you can just integrate over all possibilities. And Bayesian theorem or Bayes theorem, which give you an information how to compute this once you have the observation in terms of the observations. Now, I need to make this remark. I said that I have assumed that we have observation at every time. So remark. If observations are available every L steps. So not every step, but only every L steps. Then we can apply Chapman-Kolmogorov L times before the assimilation. It's not very precise, but it means replace what I call P by P power L, or applied L times. So if you have your system, but you have observations only here, here, and here, what you do, you evolve freely your system, which is what we do at this step. We focused L times, and then you assimilate. This is quite natural. So it's just replacing in the formula. I should do composition L times. So you do this L times, and then you assimilate. And now what happens if your observations are not at regular intervals. Then it's not a problem with what I have introduced, because, and so suppose your observations are not regular, are like this. And the notation I introduced was for that purpose. This n dependence means sometimes you iterate freely 3 times, and the next time you iterate freely 4 times. And with this formalism, now it's no more time independent. It means the number of times you iterate is going to depend on the interval between 2 observations. So you can use this formalism even if the measurements are not at regular intervals. Of course, you have to be careful, but a priori, you can do it. Is there any question? I don't want to write the details. I think it's understandable that either you iterate a regular number of times, this free evolution, L times, or if it is not even regular, then you iterate the necessary number of times. Okay. Keep in mind these 2 formulas. So what is going to happen with Kalman filter? We are going to fix a certain evolution, the simplest one, which means I can replace this by a very simple expression. And we have already seen these expressions. This is the Kalman gain formula I have introduced. 3.2. Kalman filters. But now it's easy. So additional assumption. What are the additional assumptions? The psi n, it was a model error. Follow the normal distribution n0 q. This was called model noise or model error. The f of x, it's going to be, f was related to the evolution. It's simply a matrix applied to x plus a vector, which is called a drift. So where D is an n by n matrix, and B is just a vector in Rn. So you can see it's very simple. I don't like to call it linear because for me, this is not linear. We have a linear term, but plus this shift. And the observation operator, which was h of x, is simply a matrix applied to x. So h is now a matrix m times n. So you can see we have many assumptions. But this is, let's say, the standard or the easiest model, something linear or linear plus constant term, a linear observation. This is normal centered at 0. And I have the previous observation error also 0R. So the Kalman filter. Corresponds. So, linear and autonomous, now I take it. Autonomous system. Even though I don't like the word linear in this case. Autonomous because there is no dependence on n, there is no dependence on time. So let me just emphasize it, no dependence. on n. This is why it's autonomous. So we have simply now xn plus 1 is this 1 plus d xn plus b. The 1 is what I had introduced before, plus psi n. And the yn is given by this matrix. I don't know why sometimes I put exponent, sometimes an index. Certainly, I should put exponent everywhere. But okay, you can correct this. Okay, so this is the model. And now we are just using all the things we have learned. And there will be an additional assumption. We shall assume, okay, it will come later. So I recall something we have introduced. We call that if xn follows a normal, shame on you. If a random variable follow a normal distribution centered at a certain point with a certain covariance matrix, no, we haven't proved it, but it's easy to prove, and it's something known. Then xn plus 1 follows a normal. So probably I should not write recall. Some of ocean. This is something we learn in probability. Whenever this follow Gaussian distribution, this follow Gaussian distribution of mean 0, this is just a constant, and the sum of two random variables, independent random variables, following a Gaussian distribution is again a normal distribution, so Gaussian. The mean, it's quite clear. Take the expectation of this. The expectation of this one is 0. This is just a number. So it's constant, and you end up with the expectation of xn. But the expectation of xn is here. So you end up with this. And then you need to work just, it's an easy computation. And probably this is a good exercise. If you have not done this already in a probability course, sum of two Gaussian distribution follows this. Yeah.
For the right side of the normal distribution, so 1 plus dp, so like if we write the principles on the right, it won't be the number instead of matrix.
No, this one is identities. So this is a matrix. A matrix, it's a product of three matrices, all of dimension n times n, plus another matrix. So everything is this is a matrix. This is a vector. It's a matrix applied to a vector. Here, the one is identity plus a vector. So this is a sum of Gaussian variables. It can be checked. So we know, but look, there is an assumption. We know that if this one follows a Gaussian, then the next step is also a Gaussian. And the second point now, it's really, we recall from what we have seen last week. If x focused follow a normal distribution x bar f pf, then when we apply, now I'm dealing with the second step. If the focused follow, oh no, yeah, it is a second step. If the focus follows a normal distribution, the analysis, and I recall it at the beginning of this lecture, the analysis follow a normal x bar a PA. And we have an explicit formula for this. PA is PF minus this HPF. This, it was already on the blackboard at the very beginning today. X bar F minus K of Hx bar F minus Y ops. And K is the Kalman gain matrix. Okay. We can just copy what was today at the beginning. Kalman gain matrix. So this is easy when you have this evolution, and if the two, you have two Gaussian, the evolution give you a Gaussian, then based on this formula, which was the one we had on page 46, 48 last week, we obtained that the analysis is following a Gaussian distribution with this expression. So now if we summarize, and I told you we would finish Kalman filter today. So if we summarize, it's an algorithm. What is the missing part on the blackboard? There is one small detail which is missing. If I want to write this systematically, I need an initial condition which is also Gaussian, because look, if I take n is equal to 0, the evolution of your system at time 1 is given by its evolution from time 0. But I can use this only if the previous step, it's Gaussian. But the initial condition is the initial condition. So you have to assume that it's a Gaussian distribution in order to follow this. If you take an initial condition which is not Gaussian, at least you cannot apply this first step. So it's, if we summarize, if x0, and this is something I need to impose, follows a normal distribution x bar 0 p0, we impose it. Because it's not given by the algorithm. And in fact, I should write, if I want to have a general formula, I should write x0 analysis follow n, but it's the same. It's just a convention of notation. X0 analysis, p0 analysis. Then I can write xnf follows a normal normal. I'm just copying what is already on the blackboard. 1 plus d apply to x n minus 1 a plus b 1 plus d. So we get the focus from the analysis of the previous step by the evolution, and xn analysis follows the normal of. If I want to just use, I should give a name to this. This becomes xn bar focused. And this becomes Pn focused. So this is a new name I'm giving to this. And now I can just write for n bar focus minus k, I copy this minus k, and I need to put an n. So I have just copied the formula which is here, but I need to be careful that there is an n dependence somewhere. And here, I hope I haven't done a mistake. What is, I still need to write with kf, but kn. So this is natural to call this now x bar n analysis, and this one is Pn analysis. And who is Kn? Everything is well defined because this one is from the previous line. H is the evolution. This is from the previous line. We have the observation. Then Pn is from the previous line, Knh. This and Kn. Then I can just copy what is there. Kn is this. It's here. Pnf H times HP NF HT plus R. This is a Kalman filter. This. And now you can see it's a closed formula, which means you can put this in a computer now. Because the only input are these observations. But once you have introduced H, so this observation operator, once you have introduced, or maybe I can, what are the ingredients? You need a D, which is, and a B, which corresponds to the evolution of your system. So this is something you choose. You need this observation operator. You need the initial condition. So the initial condition, you have to impose it. And now you can see why I have just written with the A, because with this A, I can directly use this line for n is equal to 1. This, I put the A here. Right. So you need this initial condition, D, B, H, and then you have the observations. But once, okay, you have two more things. You have Q and R. But once you have introduced these ingredients, you can just do this. It's essentially a multiplication of matrices plus this inversion. What is complicated is this inversion. But still you can code this process. And it's available at many places. You don't have to do it by yourself. But you can see now why Kalman filter is something which is easily implemented because it's a closed formula. Once you have introduced the ingredients, you just do it iteratively for n is equal to 1, then n equal to 2. You need to do 3 steps. You need to compute this with kn, this with kn, and so on. But it's a closed formula. Okay, I stop here for today. I'm glad that if you observe, the Kalman filter was very simple because we had already introduced everything. The Markov processes, we have introduced this already 2 weeks ago, plus what I have done last week with this example, and we get it. So next week, I'm going to introduce 2 other basic algorithm. One which is about variational approach, which is related to what we have already done in the first or second lecture. And then one which is called the particle filter. I know it's dense. You don't have to understand everything. Try to figure out what is going on. And I mentioned 1 or 2 exercise, for example, this one can be done, or a few things that I mentioned last week. And I do it by group. You can work together. It's more fun than just alone. Okay. Any question? Yes, Vic. No question? Okay.
Sorry.
Yes.
I think there is a D missing.
There is a D missing where?
Before Q.
1 plus D. Yes. There is a D missing. Please don't forget the D. Something else?
No.
No.
Maybe not.
Okay.